let's take just a moment until he gets back and walk through what we've talked about so far in the development or the evolution of the model of the atom. And remember, I want to remind you that a model is just a way of understanding something. It's not meant to literally depict all the time, but it's a way for us to understand something. And what we've seen with Rutherford and his experiments, and what we're going to see now as we go to Niels Bohr and his model of the atom, is each individual person taking something new that's been discovered about the atom and trying to put it physically in a way that we can see and understand, so that we can better appreciate and maybe even make future advancements on our understanding of what the model is, what the atom is. So if we look back to previous models of the atom as continuous whole, pieces look like something like billiard balls or solid spheres of material. Whether it's discontinuous or continuous theory of matter, this would be more of a discontinuous theory of matter type of looking at it. But going from this type of presentation, we've then moved on to, welcome back. How was Josh? Mr. Weber? Okay. A plum pudding model that looks at the atom as being, the dough as being positive, and within that dough being little chunks of negative charge. Looks like something from Svengoolie, but some negative charge there, so that this is a way of understanding the matter. Then we moved on to the Rutherford model, which was the idea that there was a nucleus, and I'm just going to draw one piece as the nucleus. We know now that there are multiple pieces, but he thought that that was just a positive nucleus, and around that nucleus there were moving orbital electrons. Part of what we didn't necessarily go into detail, we talked about the nucleus and the electrons moving around that center, but what Rutherford's model basically said that there was an orbit where the electrons moved around. And his model primarily said that there was just one orbit. So there was these electrons that were orbiting and moving all around in 3 dimensions. This is a 2-dimensional depiction of a 3-dimensional model. But that there were electrons that were orbiting around the nucleus. The next step in the evolution is what we're going to talk about today for Niels Bohr. And what Bohr came up with is what we know as the heliocentric type of model, or the multi-orbital nuclear model, where there is a nucleus. Again, I'm just going to draw it as one solid piece. We know that there are protons and neutrons there now, because by this point neutrons hadn't been discovered. But the addition to the evolution of the model is that there are now going to be multiple orbits of electrons. And so Bohr's contribution and how he came up to that with this is, we're going to talk about this in just a moment, but that there's a center nucleus that contains the positive charged protons and the neutrally charged neutrons. And around that we have orbiting electrons, but they're orbiting in multiple orbits, not just one single orbit, like Rutherford thought, he envisioned. Part of this came about because of some observations through experimentation involving light. That's why we took the last couple days talking about light and what light is, and how light is actually made up of multiple wavelengths rather than singular wavelength. Like when we see a color, we often see color as a combination of wavelengths. If we had one distinct wavelength, we would have one distinct color. When we have multiple wavelengths, what we see is the combination of those colors. For example, when we see a rainbow, what we're seeing there is the light, the white light that we normally see, which is a combination of all different colors, going through a prism and being refracted and being broken up into its different wavelengths. And so through that we see certain colors in certain bands. We're actually seeing the components that when combined together make up white light. So what Bohr did was he recognized in the lab that whenever he would excite, and by exciting what we mean by that is add energy to, so he'd add energy to atoms, and this adding energy to the atoms would add energy to the electrons, which were buzzing around the nucleus. And he would add energy to these atoms by adding either electricity or by adding heat. When you heat something up, you're adding heat energy to it. That added energy makes things, well, generally makes things move faster, except sometimes it's a little bit too warm. It makes students move slower. But heat is a form of energy, and when it has energy, there's something has to happen to that energy. Sometimes things move faster, and sometimes there are other consequences. What he noticed in the lab is that when energy would be added to these electrons, over a period of time, they would get excited, but then they would become de-excited. They would lose their energy and fall back in. Let me walk through the book and keep on the notes, because there's lots of things going on in his experiments here. What he noticed that whenever energy was added, passing electricity to these atoms, he was noticing that light was being emitted. When you would excite the atom, light was being emitted. And he noted that every different type of atom emitted its own light, its own appearance of light. Like there are different colors, different atoms. When you heated them, or when you passed electricity through them, you excited the electrons. You would see that shortly after that, you would start seeing colors, wavelengths of light coming out from the atoms. And that each different element had its own color that's being emitted. Now, as I just said, that color that you would see was actually going to be various wavelengths of light that were being combined. And so by using spectrometry, which is the science of and also a device which goes through and breaks up light into its different frequencies, it was soon discovered that different elements gave off different wavelengths of light. The component pieces of light that make up what you see, they each gave off distinct individual bands of wavelength, and that those wavelengths were consistent. In other words, if you look in your book, as an example here, it gives hydrogen gas. The middle of the second paragraph on page 111. It says that whenever he was looking at hydrogen gas, he saw a purple light. That purple light later was found to be composed of exactly 4 different wavelengths. And they list them there as 410 nanometers, which is violet, 434 nanometers, which is indigo, 486 nanometers, which we call blue, and 656 nanometers, which is a reddish-orange color. So even though he saw this purple gas being emitted, this light purple color of light being emitted, it was actually made up of 4 different wavelengths. And that every time he looked at excited hydrogen, the color was the same, and the makeup of the individual frequencies of light that were being emitted were exactly the same. So that atoms emit their own individual wavelengths of light, but most of the wavelengths are within a range. It'll make more sense as we go through what's actually happening here, because we're going to find out that what's happening is not that light is being emitted when the electrons are excited. We're actually going to figure out soon that light's being emitted when the electrons are being de-excited. So the light that you're seeing is when electrons are being pushed out to another orbit, and that's what happens. We get away from those for a minute. When we have electrons moving around the nucleus and we add energy to them, what was discovered is that the electrons move to orbits that are outside, other orbits. We're going to find also that orbits can only contain a certain number of electrons. So what's happening, let's say that this is the 1s1, 1s, or 1s, 2s, 2p ring. You don't expect to know what that is today, but that this orbit can contain 6 electrons. Let's say that there were only 5. Or maybe a better case, this might make more sense if we leave it and say that there's another orbit out here which could exist but does not yet exist because there are no electrons to be in it. If we add energy to this atom, the energy is going to come into the electrons, and one of these electrons could, when it becomes excited, move from this orbit, move out to the next orbit. The electron would actually move to another ring, if you will. There aren't rings, not racetracks there, but this electron is orbiting around the nucleus. When it receives energy, it's going to become excited. That's what it's called when it receives that energy, and it's going to jump out to another ring. It's going to come out farther away from the nucleus. It's going to take a place that didn't have electrons before, but it does now because of this excitation. Well, the energy is added to that electron, it moves out, but then what happens is it's going to fall back in. It's going to go back to a natural state, but before it can go back to where it used to be, the reason it came out was because it has extra energy, more energy than it normally has in its natural state. The electron moves out because of that extra energy, but yet this is an unstable position. It's not where it's supposed to be, right? It's supposed to be in this ring. So after receiving that energy and after being excited and moving out, what's going to happen is the electron is naturally going to collapse back in to where it's supposed to be. It's in the orbit that it's supposed to be at. There's now a vacancy here that needs to be filled because this electron has moved out to another ring. When this electron falls back in, it can only do that by getting rid of the energy that it's been given. And the way that it gets rid of the energy, let's say that it was heated up, so it's taken heat energy to accelerate, but when it falls back in, it's going to release light energy. It's going to emit light. And that's what actually Bohr was seeing. He was seeing these electrons that move out as they fall back in, as they collapse back in, or as they become de-excited and fall back in. As they fall back in, they emit light energy. Part of the uniqueness of this, or the actual novelty of this experiment, is that every time that it did this, it would emit light, but it would emit light in very specific wavelengths. It wasn't random. It wasn't, we're not sure what colors we're going to get. We're going to get a net color, but it's going to be a combination of very specific wavelengths of light when combined together equal that net color. And this is the primary way that scientists use, and you'll see this in the book, this is the primary technique that's used to say, okay, you're looking at a star way out in space. What is that star made of? How do they know that it's made up of this percentage of one gas and this percentage of another gas and so on? Is because they look at the light that they receive from that star and they break it up into different spectrums and they identify the elements that are in it based upon this technique. And so you can tell the makeup of, for example, stars by the light that it emits. And this is one of the techniques also that's used to identify virtually everything, is to excite it, and then when it's excited and the electrons fall back into their normal orbits, to see the spectrum of light that's emitted, and that allows us to identify the elements. So that device, it's mentioned on the bottom of 111, the spectrometer, that's the device that lets you figure out what the individual wavelengths of light are that are emitted. So Bohr's contribution, multiple orbits, the idea that an electron can change orbits, but the idea that they change into discrete orbits. There's not an orbit between this one and this one. It's not a subjective, arbitrary thing. That there are defined pathways, if you think of it that way. There are defined courses around the nucleus, and that electrons exist and they orbit only in those defined spaces. So, what gets kind of weird about all of this is that not only can electrons only exist in these orbits, or let me put it this way, not only can electrons only orbit in these orbits, but they only exist in those orbits. This is called a quantum phenomenon. It's a quantum issue. There's discretely, it's either here or it's here. And we can say that electrons go from here to here, and that electrons go from here to here, but yet we can only prove it when they're here and when they're here. We've yet to be able to determine exactly where the electron goes when it's not in an orbit. It's one of those phenomena where it almost instantaneously moves, and we've never been able to isolate an electron to be in a place other than those. We're not sure if it ceases to exist and then re-exists when it reaches the inner orbit, or whether it's just something we haven't been able to map yet. But that's one of the theories, is that the electron actually ceases to exist when it's between orbits and re-exists when it falls into the new orbit. So I don't know if that interests you. I know it's Monday morning. I know it's also morning. I know it's first period. I know for some of you, you're having a lot of difficulty this morning. I don't know whether I need to start remembering how to juggle. I used to juggle pretty well back in college, but I haven't done it in a long time. Some way to make this interesting. You could say, hey, pretend these are orbits. Look out, I'm excited. I need to get de-excited, bring it back. Look at me, I'm emitting a photon. No. So, let me get back on note. The quantum mechanical assumptions from Bohr actually are pretty mathematically intense. And there is a pretty detailed description of what he was looking at and what he found on page 113. I may come back to this. My sense is that if I were to get into this right now, the quantum mechanical model of the atom, Bohr's math, because the math that most of what Bohr did here was all mathematical. I'm not sure, even though we know we're going to go to the next model from Bohr's model, and we know that Bohr's model is not technically correct, just as this wasn't technically correct, but it gave us a starting point from which to come up with plum pudding, which wasn't technically correct, but it gave us a stepping point to go over here to the Rutherford model of the atom, which is a nuclear model because it has a nucleus, which isn't technically correct because we realized from Bohr and all of his mathematics, which was incredibly complex and is still used today. How Bohr figured out this whole thing with using mathematics, not with chemistry, but he figured out chemistry using math, because this is mostly physics actually. But the mathematics that he used to figure this out is still used and taught for chemists at higher level chemistry before we get to the next level, because in the same way this model from Bohr lays the groundwork for us to come to understand the quantum mechanical model of the atom. But give a light introduction to what that means, or what the quantum mechanical model is. And you can see some elementary pictures of it starting on page 115 in your text. Now, in all of this, part of the difficulty is, I alluded to it earlier, is I'm trying to draw on the board a two-dimensional representation of a three-dimensional item. Right? For some of you, you can see something in 2 dimensions and visualize the third dimension and make it pop. For others, it might be a little bit more difficult of a task. For example, if I said that I was going to come up here and draw a box on the board, some of you would be comfortable if I just came up here and went, okay, I'm going to draw a box. Is this a 2-dimensional or a 3-dimensional box? 2-dimensional box, right? I've got height and length. I don't really have any depth. And I can come up here and draw something that'll make your eye think of a third dimension. Okay? And now you might say, oh, I see, you're talking about a 3-dimensional box. Okay? In the same way, when I come up here and draw a circle, in 2 dimensions, that's a circle. But if I wanted to make a 3-dimensional circle, what would we call that? What's a 3-dimensional circle? A sphere, right? Something like this globe. How would I draw this globe on the board? Now, I could, maybe in elementary school, just go ahead and draw a 2-dimensional circle like I've done on the board right there to represent this globe. But you looking at that, probably thinking, especially since it's next to the cube, a 3-dimensional presentation of the box, go, this is kind of flat. This doesn't present real life. Will give you the idea of a circle, but I've got to come up with some way to actually represent a circle. I mean, some people might do something like this. You know, kind of give you the idea that there's some depth to it. And when we move into the quantum mechanical model, we have to think in terms of 3-dimensional representations on a 2-dimensional space. So I'm going to be drawing some pictures here that are going to look like circles, but I want you to understand they're actually spheres. Okay? So I'm going to draw a circle, but I'll hopefully refer to the fact often that we're talking about a sphere. Now we're going to start building a quantum mechanical model of the atom, and there are different kinds of orbits we're going to talk about. Just as Bohr said that there's a nucleus and there's multiple electrons in different levels of orbit around it, and it looks very much like our solar system. You know, I see that map every time I'm talking to you. Behind you is a picture of our solar system where the sun would be like the nucleus and the planets would be like the electrons orbiting around that sun. But yet, even looking at it here, it's a very flat depiction, because in actuality, our solar system is remarkably a very flat, it's three-dimensional, but it still pretty much runs in one plane. Okay, not perfectly, but it runs pretty much in a planar type model. Here we're going to talk about different orbits of the atom, and that, starting right up front, is that every orbit around the nucleus of the atoms, we've come to determine, again, this is mostly done with physics and math, not from chemistry, but that the orbits of the electrons around the nucleus don't all have the same shape. In the Bohr model, you look at it and say, hey, if it's a flat model, if it's like our solar system where it is actually relatively flat, that all these electrons kind of run in a flat plane. But if it's actually in 3 dimensions, each orbit here would be like a shell. Okay? Think of it like a beach ball. Each orbit is like a beach ball, or maybe nested beach balls. And as I go through each of these different types of orbits, hopefully it'll make a little more sense. The first orbital shape, right now we're just talking about the shapes of them, are the s orbitals. S orbitals are spheres. You can see that on 115. Figure 313 shows s orbitals. It's just the nucleus, and then drawn in 2 dimensions, it looks like, again, I can't draw a perfect circle, but it looks like I'm drawing the beginning of a Rutherford, right? Nucleus and an electron orbit, or maybe even a Bohr with a nucleus and electron orbit. But what's different is that this s orbital is a 3-dimensional sphere, meaning that if the nucleus is in the center, it's not as if an electron is orbiting in a flat plane like this, but the electron exists someplace in that sphere, in that round beach ball, with the nucleus in the center of the beach ball. Okay? The electron exists and is orbiting and is moving somewhere on that shell, that outer shell. You can see in the book it has a 1s, a 2s, and a 3s orbital. Those 3 different orbitals exist, and they're nested with one another if an atom has enough electrons to require those orbits. Again, I'm kind of teaching pieces that will hopefully come together when we're done with the model. You go, oh, that's how they fit together. But for right now, if we say we had an atom that had 3 s shells, those shells would exist inside of one another. It gets kind of confusing. Again, that's part of the problem, is trying to depict three-dimensional objects all nested inside one another. But I'm not going to draw them, but you can have a 3s shell, a 4s shell, a 5s shell. There's multiple levels of this s shell, and the s shells all nest within each other. 1s, 2s, 3s, 4s, 5s. They're all inside. 1 is inside of 2, is inside of 3, is inside of 4, is inside of 5. As many as you need to account for all the electrons that make up an individual atom. Now, since we've already alluded to it, I didn't teach it in this order last time, or when I've taught this previously, but since we've already alluded to it, I want you to know that these levels of shell, like the 1s, the 2s, when we talk about the valence shells, that's the outermost shell, the outermost electrons that make up an atom, they're going to be in the highest energy levels for the most case, and we'll talk about some exceptions. But you can see the 1s shell is over here at the 1 level. See the period, the rows in the periodic table? 1, 2, 3, 4, 5, 6, 7. And the first column here, every one of these elements, they're in this column because their valence electron is in the S1 position. It's in the S shell, and it's the first electron to be in that S shell. So hydrogen only has one electron. That one electron is in the 1s1 shell, or it's in the 1s1 position. It's in the 1s shell. It's the first electron in that shell. Over here, too, you see that this one, helium, is marked as being in the s block. This is an exception. So when we're talking about the shells, helium should be over here next to hydrogen. Just as hydrogen was the exception in the metal-nonmetal determination from the jagged line. Okay, here's the jagged line, but we know that hydrogen is a nonmetal, and so if we're looking at metal or nonmetal, hydrogen should be over here. When we're looking at what makes up the shells of electrons, the orbits of the electrons, in the same way, helium is the exception, and helium should be over here. Okay, because helium has how many electrons? Helium has 2 electrons because it has an atomic number of 2. It's a neutral atom, which meant for every proton, the atomic number means number of protons. For the neutral atom, it means also the number of electrons. So it has 2 electrons. Down here, lithium has 1 electron in the 2s shell. So this is the 2s1. Beryllium is the 2s2. Sodium, its valence electron, is in the 3s1. Magnesium has its valence in the 3s2. So you see up on the top here, it's marked s block. That means that those outermost electrons for those elements are in an S-shaped orbital, in one of these spheres. Okay, again, this information is going to build, so it'll make more sense later on. But for right now, if it's in these 2 columns, or if it's helium, which should be depicted over here, and that's why on top of it it says S block just for helium, it should be over here. That if it's in the first column, its outermost electron, its highest energy electron, is in the S1 position, and its energy level is the row that it's in. Okay? So if I were to say, what is the valence electron of rubidium? 5s first, right. Strontium, right next to it, is in the 5s2. Cesium, 6s1. Okay? The s shell can only contain 2 electrons. That's the most it can hold, is 2. That's why there's only 2 columns. It's either going to be in the S1 position or the S2 position. The S1 position is always filled first. Then, let's say, remember if we moved from potassium to calcium, for example, we add an electron. Whatever the configuration of potassium is, whatever the configuration of potassium, I need to add 1 more electron to get the appropriate number of electrons for calcium. So this would be the S1. The next would be the S2. I can't add more than 2, so if I had another electron come in, it would have to go to a different shell, because the S's can only hold 2 electrons. That's not without regard. That's irregardless of its energy level. You're saying, okay, you mean the little one can only hold 2? Yes. The next one can only hold 2? Yes. The next one can, yes, yes, yes. The S shells can only hold 2 electrons. But when we count up our electrons, we don't count, and if you look over here, we have 1, 2, 3, and 4. All of those are going to be S shell electrons. S1, 1s1, and 1s2, 2s1, good morning, 2s1 and 2s2. You see that? So the first 4 electrons are going to be 1s1, 1s2, 2s2, or excuse me, 2s1, 2s2. After 4 comes 5. We said we can't get electrons, more than 2 electrons into the S shell, and all of the S shell electrons are here in these 2 columns. So over here we notice that this one is labeled the P block. P block. So what fills after an S shell and after the 1s1, 1s2, 2s1, 2s2. Next comes 2p1, the p. Now, notice on the bottom of 115, they show you what the p orbitals look like. P orbitals are often drawn like dumbbells. No, I'm not a good artist, otherwise I'd try to draw somebody in here. But it's not. It looks like more like a figure 8, more like a propeller maybe is a way to think of it. A propeller. That's a p orbital. P orbitals look like a propeller. They can hold 2, again, 2 per orbital, but there are 3 p orbitals per energy level. Now, they show the difference between a 2p orbital and a 3p orbital by its size. But if you think about it this way, let's say that this is the 2p1 orbital. At the second energy level, if I can only have 2 electrons per orbital, but I have to count for 1, 2, 3, 4, 5, 6 electrons within the p orbitals, and each one can hold 2, that means I need 3 different orbitals to hold all 6 electrons. Does that make sense? I need 3, if they can each hold 2, I need 3 of them to account for 6. Okay, work with me on this. Here we go. So if this propeller shape can hold 2 electrons, and let's, just for argument, let's pretend that they exist on the outermost edge at the same time like that. I can account for 2 electrons in that way. Trust me if I say we need to get 2 more electrons in there. How are we going to do it? We're going to add another orbital. Okay, now I've accounted for 4 electrons. But I need to account for yet another 2 electrons. I have to have another shape. Now I'll draw it like this. But this is when we start to get into the difficulty of seeing this as a 3-dimensional shape drawn on 2 dimensions. Think of it this way. If I needed to have, and I'm asking you to just kind of visualize this with me here. If I have 2 electrons, I need to count for them in a p orbital. The first 2 would kind of be flat and be in this plane right here. Okay? So here's 2 electrons forming a p orbital in this way. If I wanted to do 2 more, and let's assume they had to be equally divide the distance between these 2, the next 2 would go up and down like this. Again, in this flat plane, 2 in this way, 2 in this way. If I need to add 2 more, where would they go? They would go out towards you and back towards me. Okay? Let me try to do that maybe with a marker here. Say these 2 fingers represent 1 p orbital, these 2 represent another p orbital, and the third one is the one that comes this way in the plane. If you were trying to draw something, in graphing, let's say, you're drawing your Cartesian coordinates. You have your x-axis, and your x-axis this way, left and right, your y-axis up and down, and then you have a z-axis. Where's the z-axis? It's coming straight out of the origin, right out towards you, like that. Z is coming straight at you as you're looking at that 2-dimensional drawing. So you've got x, let me turn this way. You've got x, you've got y, and you have z. And that's how we can depict things in 3 dimensions, because we need 3 coordinates to do 3 dimensions. In the same way, these p orbitals, they follow the x-axis, the y-axis, and this third one is in and out in the z-axis. Towards you, back into the board. Okay? So again, the complication is drawing something that's actually 3-dimensional on a 2-dimensional space. It gets very difficult. If you turn over the page, it kind of shows this representation on figure 315. The 3 different p orbitals, all of the same energy level. So remember, energy levels is that larger category, which comes over here and refers to, on the periodic table, refers to the row. Everything in this row is of the first energy level, second energy, third energy, fourth energy, fifth, sixth, seventh, and so on. Okay? This is the energy level, left and right on those rows. What orbital they're going to be in is depicted on the periodic table by where they sit relative to their columns. Here are the s. Their valence electrons are in the s, in an s sphere. Over here in p, their highest energy level valence electrons are in a p orbital. S's contain, see, this is the we'll say this is the orbital shape, and this is the number of electrons that they can hold. S's can hold 2 electrons. When we get to the p, let's make this the total electrons. That's a more accurate way to think about it. Because the p orbitals can hold a total of 6 electrons, it's actually 3 times 2. You've got 3 different shapes. Each one can hold 2 electrons for a total of 6. That would be a more accurate way to think about it, okay? Because sometimes if I say the p orbitals will hold 6 electrons, some people will draw 1 dumbbell and put 6 electrons on the 1 dumbbell. That's not the case. Every orbital, every shape, every pattern can only hold 2 electrons. In the p orbitals, there are 3 distinct shapes. In the s orbital, there's only 1 location it could be, and that's on the shell, on that, you know, within that ball, within that sphere. Now, the last type we're going to do for this course, we're going to really talk about, is the d orbital. And if you look in your book, there is no picture of the d orbital, because this is kind of where mathematically the whole thing kind of goes, and it gets really theoretical, and we have to use computers to draw these, because we as humans are unable to draw in 3 dimensions what this thing looks like, okay? But the d orbitals have 5 different shapes within them, 5 different pathways within them. And so how many electrons can a d orbital hold? 10, right? The d's, these are all technically lowercase. The d's can hold a total of 10 electrons because they have 5 different orbital shapes, and within that each one can hold 2 electrons. And I said before, I don't think it's in this level for this course, but just for your own knowledge, the reason why they can only hold 2 electrons is because of the spin on the electrons. So these electrons are going to have counter rotations. You can't have 2 electrons in the same orbital that are spinning in the same direction. So 2 electrons can fit into an S shell, 6 electrons can fit into a P shell, 10 electrons can fit into a D shell. Now, another interesting thing, as we start to build the quantum mechanical model, and if you want to flip over to page 119 real quickly. 119 gives a picture of this quantum mechanical view of a neon atom. What I want you to also understand is while we have s orbitals and p orbitals, and we're going to have d orbitals, that these all simultaneously exist at the same time. All these multiple orbitals are happening. And so it gets rather confusing rather quickly. If you notice here, on the neon atom, it's neon 22. So what we're looking at, if we go over here, it's neon. Neon has a atomic number of 10. So we'd have 10 protons, 10 electrons, and in this case, 12 neutrons. But notice how the orbitals are depicted. You have a nucleus, and just reading the annotations on the diagram, you've got a nucleus that has 10 protons and 12 neutrons, okay? That's what neon 22 always has. And then we've got the different orbitals. We've got a 1s orbital, which has 2 electrons in it. And that would be the innermost blue circle around the nucleus. That sphere contains 2 electrons. Then we have the 2s orbital, which is slightly larger blue sphere. It has the 1s completely within it. Do you see that from the diagram in the book? That 1s shell is completely inside. It's completely nested inside of the 2s shell. 2s shell is another sphere, but it's bigger. It contains the entire 1s within it. And then this diagram here also shows 3 p orbitals, each one with 2 electrons in it. And so you have a nucleus, real quickly up here. You have a nucleus, you have the 1s shell, you have the 2s shell, and then you have the 2p shells in their propeller, dumbbell, three-dimensional XYZ configuration, all existing at the same time. What's kind of interesting is, I've taught this using the periodic table. In the book, they teach it, and then they use the periodic table to show you, oh, here's why the periodic table is the way it is. We've already talked about this a few times. But whenever you want to go and construct, what does the orbital pattern for any given atom look like? There's a progression that we're going to use to do this. Well, let's go ahead and first of all, let's use the periodic table, and then I'll show you another way that you can construct this if you don't have the periodic table available to you. So we're going to use both the periodic table and what's known as a slant diagram to figure out what the electron configuration looks like for any given atom. So again, if we were to use the periodic table, there is one more trick you need to know for configuring using the periodic table. We'll get to it when we're at that point. Let's say that we're going to build the electron configuration for aluminum. Okay? Now we could sit here and say aluminum, atomic number is 13. 13 protons, 13 electrons, and let's say it was aluminum 27, we have 14 neutrons. Our issue now is electrons. How many electrons do we need to account for? Aluminum in a neutral atom, has 13 electrons. We're going to build the configuration of aluminum. We're going to do that by starting way over here at the first energy level. Because here's the deal. Even though we can tell from the periodic table very quickly that aluminum has its valence electrons in the 3p1 position. 3 because it's the third energy level, p because it's in the p block, p1 because it's the first of the p to be filled. Okay, so it's the 3p1 as its valence. Again, it'll make more sense as we do this a few times. I have to account for every electron up to that point. Where are all the electrons at? And what we do is just start with the basic configuration and just keep building, add one electron at a time. What can you tell me about in the first energy level? There's a 1s1 and a 1s2 electron, right? The way we're going to depict that is the first energy level, actually there's, some of this is shown at the bottom of 119. So a 1s2, what does this notation tell me? I have 2 electrons in the 1s shell. It's full, right? I can't have more than 2 in the 1s shell. I'm building aluminum. So I've counted for the first electron, the second electron. The third electron is going to be here, which is in the second energy level, second row. So it's a 2s, 2s1, 2s2. I've got 2 electrons in the 2s orbital. So 2s2. So this accounts for the first 2 electrons. This accounts for the second 2 electrons. Now, reading from left to right, so 1s1, 1s2, 2s1, 2s2. What's the name of this electron? This next electron? Its position is going to be the 2p1. 2p1, 2, 3, 4, 5, and 6. I have 6 electrons in the 2p orbitals. 2p6. We're not done because we're not to aluminum yet. Start back over at the beginning again. We were at 2, now we're at 3. 3s, 1 and 2. We have to count for both of those. 3s, 2. Continuing across. Boom, aluminum. We're home. We're the one we're trying to figure out. This is going to be the 3p1 electron. 3p1. Okay? We've basically given the address of every electron that's in an aluminum atom. The electrons, how many do we have? How many do we need total? 13. How many have we accounted for? 1, 2, 3, 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. The electrons exist in the 1s2, 2s2, 2p6, 3s2, 3p1 orbitals. We'll pick it up there tomorrow.